so let's try to answer questions for section A, chemistry 112, a paper which was written in 2025. This is the final exam. So what you need to know is that this question paper consists of two sections. That is section A and section B. For section A, you're supposed to answer all the questions, and then for section B, you have to attempt any two questions, but for question B1, it is compulsory. Okay, we also have the useful data for the gas constant, which is R, as well as pressure, and the useful formula, specifically the Arrhenius equations. So we have question A1, which is saying the rate constant for a reaction increases from 2.1 multiplied by 10 to the power negative 3 per second at 298 kelvins to 8.7 multiplied by 10 to the power negative 3 per second at 308 kelvins. Calculate the activation energy using the Arrhenius equation. Then R is equal to 8.314 joules per mole per kelvins. Then this one is carrying 5 marks. So what I'm going to do here, let me just collect data, and then we can know now which formula we are going to use. Okay, so we have the rate constant, which is K1, which is equal to 2.1 multiplied by 10 to the power negative 3 per second. We also have temperature number 1 in kelvins, which is 298 kelvins. But let's have an example. If they have given you the temperature in degrees Celsius, let's say 27 degrees Celsius, what are you supposed to do? Always you need to convert it into kelvins. How? Temperature in kelvins is equal to temperature in degrees Celsius plus the absolute zero temperature. So usually the absolute zero temperature is 273 kelvins. This is the absolute zero temperature. So you can just add 27 degrees Celsius plus 273 kelvins. Then here I'm going to have 300 kelvins. So this is what you're supposed to do always. Okay. So apart from that one, we also have K2 and T2. So for K2 is equal to 8.7 multiplied by 10 to the power negative 3 per second. Then for T2, we have 308 kelvins. So this is what we have. Apart from that one, we also have R, which is 8.314 joules per mole per kelvins. So this is what we have. So according to the information that we have, which formula are we going to use according to these Arrhenius equations that we have? Is it the first one, second one, or third one? So we are going to use the third one. This is because we know to say that we have K2, also have K1, T2, T1. But here, in the formula which I'm going to use, I'm not going to include the negative. I don't want to work out with a negative. So if I want to eliminate this negative, meaning to say I need to interchange these values. So I'm going to start with T1 and end with T2 if I want to eliminate a negative here. But if you don't want to eliminate a negative, you're also going to arrive at the same answer. So we have ln K2 divided by K1, which is going to be equal to the activation energy divided by the gas constant, and then open bracket 1 divided by T1, 1 divided by T2. So this is what we have. So on this one, ln open bracket K2 is 8.7 multiplied by 10 to the power negative 3 per second. Then divided by, here we have 2.1 multiplied by 10 to the power negative 3 per second. Then this is going to be equal to activation energy divided by the gas constant, which is 8.314 joules per mole per kelvins. Okay, so this is what we have. Then open bracket 1 divided by T1. So what is our T1? Our T1 is 298 kelvins. Then our T2 is 308 kelvins. So this is what we have. So from there, let me do the computation for this side here. So when I do the computation, what am I going to have? So I need to say this one is going to be cancelled with this one. Actually, 10 to the power negative 3 is the one which is cancelling with that one, not that one. Let me do this. Okay, so that is the way it's supposed to be, and this one is cancelling with that. Then I can say, and also the units, they are cancelling each other, so 8.7 divided by 2.1. Then we can say ln, then the answer that I'm going to get inside here. So what am I going to have when I do the computation for that part? So I'm going to have 1.421, which is going to be equal to, so I can do the computation inside here. So I can say 1 divided by, so I need to say open bracket 1 divided by 298 minus 1 divided by 308, and then close bracket, and then here I'm going to have 1.09 multiplied by 10 to the power negative 4, then activation energy. So remember, I also have this one here, the gas constant, which is 8.314. Then here we can say joules per mole per kelvins. Then from there now, I just have to cross multiply here, then divided by the same one here. So our activation energy, when I divide, is going to be, actually it's going to be 1.08 multiplied by 10 to the power positive 5, and this one has to be in joules per mole. Now, most of the times you're going to find that this activation energy is expressed in kilojoules per mole, and you know to say that kilo is equivalent to 1000. So I just have to divide the same value which I have here by 1000, so that I convert this one in kilojoules. So my activation energy is going to be 108 kilojoules per mole. Then from there, we are done for the first question. Let's see the second one. So for the second one, it is saying for the reaction, for the following reaction, the initial rate formation of iodine was found to be 1.5 multiplied by 10 to the power negative 3 moles per decimeter per second. So we have this equation here. Now, one thing that you need to know here is that this is the consumption here. This is the rate consumption. This is the rate consumption. And this is the rate formation. I'm going to explain why. So when it comes to the reaction, the way the reaction, if the reaction is proceeding forward, you're going to find that there will be the consumption of the reactancy, and the products are going to be formed. That's the reason why we are saying the rate formation. So the products are being formed, or there is increase in the products and reduction in the reactants. So that is one thing you need to know about the forward reaction. Now, according to the ratios that we have here, the ratio that we have here is 1 to 2 to 2 to 1. So in this question, we have been given the initial rate formation of this one here, which is iodine. So now the questions are saying, or the question is saying, calculate the initial rate of formation of sulfate ion. So we are calculating this one here. So we need to compare it with this one by using the ratios. So we have 2 to 1. Then in terms of the initial rate formation of iodine, we had 1.5 multiplied by 10 to the power negative 3. So since it is 2 to 1, meaning to say the rate formation of sulfate ion is twice to that of iodine. Let's hope that one is clear. So meaning to say, for us to answer this one here, I'm just going to say the initial rate formation of sulfate ion is going to be equal to twice of the rate formation of the iodine, which is 1.5 multiplied by 10 to the power negative 3 moles per decimeter per second. So when I multiply, I'm going to get, let me just write it here. So when I multiply, what am I going to get? So I'm going to get 3.0 multiplied by 10 to the power negative 3. Then the units are the same. Okay. Then per second. So this is going to be our final answer. Okay, so for the second one, it is saying we need to calculate the initial rate of consumption. So we are looking at the consumption, this side here, not the rate of formation. So for the rate of consumption of peroxy diphosphate ion, so this is peroxy diphosphate ion. So what are we going to do? Still here we need to compare. So what ratios are we having here? We have 2 to, let me say not 2 to 2, but 1 to 2 to 2 to 1. So we already know the rate formation of iodine, so we can compare it with the peroxy diphosphate ion. So as you can see, it is 1 to 1, so meaning to say they are equal to each other if it is 1 to 1. So what are we going to do? The initial rate of consumption of peroxy diphosphate is going to be equal to 1 multiplied. You just have to show that you are multiplying. So 1 multiplied by 1.5 multiplied by 10 to the power negative 3. And the units are moles per, so moles per decimeter cube per second. Then when I multiply, I'm just going to have the same answer, which is 1.5 multiplied by 10 to the power negative 3 moles per decimeter per second. So this is going to be our final answer. So that is the way you're supposed to answer that. Okay. Question 3. Compound A and compound B react to form compound C and D. So just write the reaction of what is happening here. We have A being reacted with B. Then the products that we are going to have here, C and D. Now, in a reaction that was found to be second order overall. Okay. So this one is saying the second order overall and second order in A. So A is second order. A is second order, but the overall is also second order. So the rate constant at 30 degrees Celsius is 0.622 liters per mole per minute. That is what we have been given. That is the rate constant. So we can say the rate constant here is going to be equal to 0.622 liters per mole per minute. So that is what we have. Now, according to the first question, which is Roman number 1, is saying we need to calculate the concentration of A. So we need to calculate the concentration of A, or what concentration of A will remain if the reaction started with this one. So this one is the initial one. So it started with this one here. Now, what are we going to remain with? And remember, the reaction, the overall reaction here is what? Is second. So in terms of the reaction, since A is the second order, what is going to be the formula? So we can say K is going to be equal to, let me say not K, but rate. Okay. So rate is going to be equal to K, which is a rate constant, and we are going to have A to the power 2, because this one is saying A is the second order. That's the reason why I'm putting 2 here. If A was a first order, meaning here I have to put 1. If A was the third order, I have to put 3 here. That's a mandatory that you need to know. Okay. So from there, here we are looking at the consumption which is going to remain. The consumption which is going to remain when this one was used at the start of the reaction. So what are we going to do? Remember, the overall is what? Is also the second order. So what are we going to do? We are going to say 1 divided by A final, and this is going to be equal to 1 over A initial, then plus Kt. Let's hope we are together on this part here. Now, we know to say that our K here, we have been given, it is this one here. According to the question, do we have the time? We don't have the time. So meaning to say we just have to express this one in form of the function, because we don't know the time. And there's nothing that we can do for us to find the time here. So let me just erase this one here. So let me just answer it here. So we are going to say 1 divided by the final one. So we are looking for this one here, final. And this is going to be equal to 1 divided by the initial. So we started with 4.1 multiplied by 10 to the power negative 2. Then also here we have to include the units. But remember we have K, which is 0.62. Then you put also the units, then multiply by 2. So from there now we can do the computation here. We can divide. So when I divide here, I'm going to have 1 divided by the final, which we are looking for. So A final, which is going to be equal to 0.0244, then plus 0.622, then T. Then from there, what are we going to do? Since we know to say that this one here is more like an inverse, so for us to find the final concentration of A, we just have to reciprocate these. So you can say the overall divided by 1. So 1 is going to go on top, and these, they are going to go down. So let me just write our final answer here. So we are finding A final, which is going to be equal to 1 divided by 0.00, so this one has to be 0 again, then 244, then plus 0.622, then T. So this is our final answer that you need to, or you need to express your final answer in form of the function. So that is what you have to do here. Remember, we don't know the time. That's the reason why we are leaving our answer in that form. Okay. So now, for the second part, it is asking us to calculate the half-life, or what is the half-life of A. If 4.1 multiplied by 10 to the power negative 2 of A is reacted with B in excess, or if B excess. So to answer the half-life, what are we going to do? Okay. We are going to do this. We know to say that for us to find the half-life is equal to 1 divided by K, then multiplied by the initial of A. That is what we have to do here. So this is going to be equal to 1 divided by, so what is the value of K? So the value of K is this one here, which is 0.622, then multiplied by the initial value of A. We want to say that the initial value of A is this one. So it is 4.1 multiplied by 10 to the power negative 2. So I just have to multiply this one, then 1 divided by the answer which I'm going to get here. So as a result, I'm going to get 39.2 minutes. Remember, here we are having per minute, or per minutes. So this is the reason why I'm putting minutes here. If it was having something like liters per mole per second, so our answer has to be in seconds here. So half-life is measured in the unit of time. Just depend on the unit that you are using, or that the unit that is in the question. Then for question 4, it is asking us to calculate the pH of a solution of ammonia whose concentration is 0.1 and the Kb is 1.7 multiplied by 10 to the power negative 5. So one thing that you need to know here is that we are looking for pH. So pH plus pOH is equal to what? 14. Another thing that you need to know is that pH is related to the concentration of hydronium ion. So it's the negative log of concentration of hydronium ion or hydrogen ion. Then for pOH is related to the concentration of hydroxide ion. So it's the negative log of hydroxide ions. So now, if I write the decomposition of this ammonia in water, we are going to have ammonia reacting with water. Water is H2O. So we have H2O. And this is going to give us, so in this case here, water is going to act as an acid. So it's going to donate a proton. Then what are we going to have? We are going to remain with the hydroxide ion here plus ammonium ion. So this is what we have. So in terms of the ratio is 1 to 1. But we know to say that here we can calculate the concentration of hydroxide ion by writing the expression of Kb. So Kb is going to be equal to the product divided by the reactance, isn't it? But here one thing that you need to know here is that we are not interested in finding the value of water. Water is in form of the liquid. So in this case here, we don't focus on water. Water is considered to be 1 as a value. So this is aqueous. This is also aqueous. This is also aqueous. So what are we going to have? The product, we are going to have the hydroxide ion. We're also going to have the ammonium ion, then divided by ammonium. So ammonium there is this one. So in terms of the IC table, we need to draw the IC table here. So that's going to be a short one. So let me just draw it here. IC table. IC, I for initial, C for change, then E for equilibrium. So at initial we have hydronium, let me say ammonium. For initial it is 0.1. Then when it comes to hydroxide we don't have, that is 0. Even when it comes to ammonium ion, here we don't have, it is 0. Now if we use the idea of saying that for the reactants they are the consumption, and then for the product they are the late formation, meaning to say here in terms of the ratio we have 1 to 1 to 1 to 1 to 1. So here we are going to less by x, not add but less by x. So we are going to less by x. If here we add 2, meaning to say we need to say 0. We need to say negative 2x. But since we are having 1, we just have to say negative x. Then since the ratio is here, just 1, 1. Since these are on the part of late formation, we need to add plus x. So here we're going to have 0.1 minus x. Here we're going to have x, even here we're going to have x. So using the Kb expression, what are we going to have? We know to say that our Kb is 1.7 multiplied by 10 to the power negative 5, and this is going to be equal to, for hydroxide and ammonium ion is xx, and divided by this one here, which is 0.1 minus x. So for this part here, you have to assume that x is less than 0.1. So if we assume that x is 0.1, meaning to say the value here is not going to be affected. As a result, I'm going to discard x. So this is what I'm going to have. So x multiplied by x, that is x squared, and this is going to be equal to, let me just write that one. So we have 1.7 multiplied by 10 to the power negative 6. So yeah, I just have to find the root or the square root. So the value of x is going to be equal to, so when I punch on the calculator here, I'm going to have 1.3 multiplied by 10 to the power negative 3. And this one has to be in molarity, or yeah, in molarity. So this is the value of x. So meaning to say this is going to be the value for the hydroxide concentration as well as the concentration of ammonium ion. So since we have now the concentration of hydroxide ion, we can easily find the pOH. How? We know to say that the pOH, let me just use this part. The pOH is equal to the negative log of the hydroxide ion. So the hydroxide ion there is 1.3 multiplied by 10 to the power negative 3. Then when I punch on the calculator here, what am I going to have? I'm going to have 2.89. So this is the pOH, but what about pH? So I need to use this formula. pH plus pOH is equal to 14. So for me to find pH here, just have to say 14 minus pOH, which is 2.89. Then here, what am I going to have? I'm going to have 11.1. So this is going to be our final answer for this question here. And then for question 5, it is saying what is the molar solubility of hydrated zinc at the pH of 8 for KSP is equal to 2.1 multiplied by 10 to the power negative 16, 5 marks. So the first thing we need to write the ionic equation of this one here. So the ionic equation of zinc hydrated or hydrated zinc is going to be this one. So remember, we have 2 moles of hydroxide here. Then zinc has a valence of 2, so that is positive 2. Then plus, since we have 2 moles of hydroxide here, I just have to put 2 here so that I balance up with the hydroxide which I'm going to have here. So this is the decomposition equation. Now, according to the values that we have been given the pH, which is 8. Also been given the KSP, which is 2.1 multiplied by 10 to the power negative 16. So what next? We know to say that from this one here, we can easily find the concentration of hydroxide. This is the pH, but we can easily find the concentration of hydroxide by connecting it with the pOH, because we know to say that in the pOH we have the hydroxide, so we can find the concentration of hydroxide here, then calculate the solubility or the molar solubility of this one, which is the hydrated zinc. So this is pH. So for me to find the pOH, I just have to say pOH is going to be equal to 14 minus 8. Then 14 minus 8, what are we going to get? We are going to get 6. So from here we can come up with an assumption to calculate the concentration of hydroxide. So we know to say that pOH is equal to the negative log of hydroxide ion. So here you just have to divide by -1, even here by -1, so that these and these, they are just going to cancel each other. As the result here, we're going to remain with log the concentration of hydroxide ion, then this is going to be called negative pOH. Remember, pOH we have, which is 6. So here I can just express this one in terms of an exponential. Remember, this one, it has a base of 10. So this one has to go to the other side, and this one has to be the power of 10. So we are going to have the hydroxide ion, which is going to be equal to 10 to the power negative pOH. Remember, pOH is 6. So what are we going to have? So for this part, the hydroxide ion is just going to be equal to 10 to the power negative 6. Now 10 to the power negative 6 is what? This one is going to give me, what am I going to get? Just the same one. Yeah. So you can just say this is going to be equal to 1.0 multiplied by 10 to the power negative 6 molarity. So this is the concentration of hydroxide ion. So let me write now the KSP expression. So for KSP, let me do this. For KSP, we know to say that KSP is equal to this one here. Okay. So you can say products. So in terms of the products here, what do we have? So this one has to be a solid. Okay. Although it is hydrated, but it is in form of the precipitate. So it is a solid, and these has to be in aqueous. So for solids, we just ignore them. So that we're going to have here, we're going to have zinc ion. Then we're also going to have hydroxide ion. But remember, the coefficient becomes the power. And also, if we replace what we have here in terms of the solubility as S, what are we going to have? The KSP is going to be equal to, open bracket, this is going to be S. Okay, this is going to be S. So I have to use the curly brackets. This one has to be S, and this one has to be 2S. The reason why I'm putting 2S because of this coefficient here. That's the reason why I'm putting 2S, then to the power 2. So we know to say that S is in form of now the solubility. It's a solubility in short, a solubility value. Okay. Let's answer question 6. So for question 6, what do we have? So for question 6, what do we have? Given reaction, we have this one here, which is the methane. Let me say methane. Methane plus water. We are having carbon dioxide plus hydrogen gas. So the initial for methane is equal to the initial for water, which is equal to 0.1. Then carbon dioxide initial is equal to hydrogen initial, which is equal to 0.00 molarity at equilibrium. Then for carbon dioxide at equilibrium, let me say for carbon dioxide is equal to 0.040 molarity. So we have been told to calculate Kc. So what are we going to do? Here, let me just relight the, where can I relight this question here? Let me relight now the IC table. IC table. Okay, this is our IC table. So what I'm going to do here, I'm just going to focus on what we have here. So according to this question here, let me use this color here. We have methane, and the initial concentration of methane is 0.1, and this is also equal to the initial concentration of water, which is also 0.1. But when it comes to carbon dioxide at initial and hydrogen at initial, it is 0 and 0. Then here, what are we going to have? Since this reaction is proceeding, it's a forward reaction, so here we're going to have minus x, even here minus x plus 3x. The reason why I'm saying plus 3x, this is because we have a 3 here, then these, they are just having 1, 1. Then in terms of the equilibrium, at equilibrium, carbon dioxide is having 0.04. But for these, what are we going to have? We're going to have 0.1 minus x. Then here 0.1 minus x. Then for this one, since it is having 0.01, so meaning to say x is going to be equal to 0.04. That is what it is saying at equilibrium, isn't it? At equilibrium, this one is having that. Then from here, we have 3x. That is for hydrogen. Now, the question is asking us to find Kc. So we need to write the expression for Kc. So Kc is going to be equal to product divided by the reactants. So in terms of the products, so steam here, let me say water is in form of steam, so it is going to be aqueous. So that's the reason why we are including it here. So we have the product, which is carbon dioxide. We also have hydrogen, which is to the power 3. Remember, this one is different from solubility, so no need of us including the 3 during the calculations. Then divided by the reactants. So we have methane, we also have water. Then from there, now what are we going to have? Since we know to say that x is equal to 0.04 at equilibrium, so we can easily find the concentration of this one here, the concentration of this one here, the concentration of this one here. How? We can just say 0.1 minus x, and x we know to say that is 0.4. And this is going to give us what? When I do the computation, I'm going to get 0.06. So this is the concentration of methane. Since they are having the same formulas or the same equations, meaning to say even this one is going to be the concentration of water. We already know the concentration of carbon dioxide at equilibrium. But what about this one? I'm going to say 3 multiplied by 0.04. This is for hydrogen, and what am I going to get? I'm going to get 0.120. So you can do the computation here. So for carbon dioxide, that is 0.04. For hydrogen is this one, which is 0.12 to the power 3. Then divided by, for methane, it is 0.06. For water, it is 0.06. Then close. So our Kc, when I do the computation, it's going to be 1.92 multiplied by 10 to the power negative 2. And this one here doesn't have units. So this is how you're supposed to answer that. Okay. Let's answer question 7. So for question 7, it is asking us to calculate the molarity of a 25.6% by mass aqueous solution of sulfuric acid. For the molar mass of sulfuric acid is 98.08 grams. So remember, the molar mass has to be in grams per mole. So this one is supposed to be like this. So what do we have? So here, we have 25.6% by mass of sulfuric acid. Apart from that one thing that you need to know here is that this one here can also be equal to 25.6 grams, since it is saying by mass. So it's equal to 25.6 grams. Now, what is the mass of water? The mass of water is always 74.4 grams. Now, from what we have here, we can say, where is this one coming from? This one, same 74.6. Where is it coming from? It is coming from the percentage. We know to say that the percentage is always add up to 100%. So if we say 100% minus 25.6, what are we going to have? We're going to have 74.4 grams. So meaning to say this one is going to be, or you can say percent, which is same as it, because this one is going to be the percentage by mass, which is going to be equal to 74.4 grams of mass of water. So this one here is for sulfuric acid and the remaining is part of water. And how are we calculating that one? You less 25.6 from 100%, and we're having 74.4%, and which is going to be equal to 74.4 grams of water. So now for the first part, let's deal with finding the number of moles of sulfuric acid. Since we know to say that the percentage is same as the mass, so the number of moles is going to be equal to the mass divided by the molar mass. So the mass we have, which is 25.6 grams, then divided by the molar mass, which is 98.08 grams per mole of sulfuric acid. So the number of moles or moles of sulfuric acid is going to be equal to, so when I divide here, I'm going to get 0.261 moles. So this one here, these are the number of moles of sulfuric acid. So for the second part, we have the mass of water, which we have to convert it into grams. So we have 74.4 grams. So this one we have to say 74.4 grams divided by 1000 grams, because we know to say that 1 kg is equivalent to 1000 grams, and this is going to give us 0.0744 kgs, and that one is going to be the mass. So we have the mass as well as the number of moles. Okay. So to calculate the molarity, remember that one, the molarity that we are calculating is the molarity for L, not the molarity for R. So they are two different. The molarity for L and the molarity for R, they are two different. So for the one for L, it is the one that deals with kilograms. Then the one for R is the one that deals with osmoles. So we are calculating the molarity, which is M, osmolarity M, and this is going to be equal to the moles of solute, that is the moles of solute. So this is the formula that you need to know. The moles of solutes divided by the kilograms of solute. So kilograms of solutes, and this is going to be equal to the moles of solutes we have calculated to be 0.261 molarity divided by the kg of solute, which is 0.0744 kilograms. And this is going to be equal to, when I divide, I'm going to get 3.51 moles per kilograms. So this is going to be our final answer. Let's answer question 8. Just love this part. Okay, so for question 8, it is saying consider the compounds shown below. Then Roman numeral number 1 is saying name compounds A, B, and C. Start with A. So for A, we have the amine group here. We also have a double bond there, which is the carbonyl group. So you can identify this one as the carbonyl group, which is G. Then this is the amide group, or the amine group, just depend on how you want it to be, the amide or the amine group. Then we also have the last part here, which is the methyl group. So this is what we have. Now, one thing that you need to know here is that how many carbons do we have here? So from here, we have one carbon also have another carbon here. So in terms of writing, we can say we have CH3, that is for this part here. Then this one is linked to a carbon, which is the carbon at the center here. Then here there is a double bond. Then we have oxygen there. Then we also have another bond here for this one here. So we can say, let me say, we can say we have the amine group here, which is NH2. So how many carbons do we have here? We have 2 carbons. So since we have 2 carbons, meaning to say this one has to be the eth. This one has to be the eth. Now, which compound here or which functional group here is dominating the other? One thing that you need to understand here is that this compound here, which is the amine group, is dominant compared to these other compounds like the carbonyl group as well as the methyl group. So to name this one here, we are going to follow the functional group which is dominant. In this case is the amine. As a reason, we are going to say this one is going to be the methane amide. Okay, so it's going to be for structure A, it's going to be the methane amide. Okay, so methane amide, that is for the name of A. Then what about B? So for B, like the way I was saying, let me start with the alkanes. So for alkanes, whenever you see a dot, okay, so whenever you see a dot, meaning to say this is the methane. Whenever you see a line like this one here, meaning to say this is ethane, this is because we have carbon number 1 and carbon number 2. So this is how we count. So let's count the number of carbons in the longest chain here, so that we name this one here. So we name for this, we name the number of we name the compound according to the number of carbons in the longest chain. So if we count this one to be 1, this one is going to be 2, this one is going to be 3, this one is going to be 4, this one is going to be 5. Let's see if we use this way. This one is going to be 1, this one is going to be 2, this one is going to be 3, this one is going to be 4. So this is the shortest one, so we can't consider this one. We need to consider the longest chain. This one is going to be 1, this one is going to be 2, this one is going to be 3, this one is going to be 4, this one is going to be 5. So in terms of writing this one, in terms of the structure, we can say this is carbon number 2, and these are methyl groups. So we have the methyl group here. Okay, we have the methyl group there, and then we also have another methyl group here. Then what are we going to have here? We are going to have another bond here. But remember, for this one here, which is carbon, it has the valence of 4, and also the bonds has to be 4. So that is one thing that you need to know. So I have written this carbon here, which is carbon number 2, and then carbon number 3 there. Then what am I going to have? I'm also going to have the methyl. Then from here I'm going to have another carbon. Then from here I'm also going to have another carbon there. So how many carbons in the longest chain? So here you just have to fill these with the hydrogen bonds like this. The hydrogens, I mean. So this is the same structure. The one which I've drawn here is the same structure which we have here. So if you count, the longest chain is 1, 2, 3, 4, 5. So since this one here, it is an alkane. It is an alkane, meaning to say 5 means what? Pentane. That is one thing that you need to know. So meaning to say this one is going to be pentane or pentane. Pentane. So this one is going to be our answer for this one here. But you need also to do a research on this one. Maybe I can give you a wrong answer on this one, but this is how you're supposed to answer it. Then for the last one, this one here, whenever you see the hydroxyl group on a cyclic compound, so this one here, the cyclic compound, which can be a benzene, which can be in a benzene form, you just have to know that this is the phenol. Okay, so this is the phenol. So meaning to say for C, it is going to be phenol. That's all. Then for Roman number 2 is saying which compound will be more soluble in water, and state the type of interactions that will exist with water molecules. So the molecule which is going to be more soluble in water is this one here, which is methanoamide, or let me say not methanoamide, but methane amide or methane amine. So that is the one which is going to be soluble. So I can say compound A. So I have to state the the interaction which is going to exist between the water and the same compound A. So compound A. So in terms of the interaction, this one here can form where is the structure? This one here. For this amine here, it can gain a proton and then become a charged one. Okay, it can gain a proton and become a charged one, which is going to be positive. And this one here is going to interact with water to form the hydrogen bonds. It's a dipole to dipole interaction. So we can say dipole to dipole interaction. That is dipole to dipole interaction. That is the one which is going to be formed with water molecule. So let me just write molecule here. Or if you don't want to say that, you can say hydrogen bonds. So the hydrogen bonds are going to exist there. So the hydrogen bonds, or hydrogen bonding. And then you are done. So for section B, I'm going to answer it in the next video.